Hello, my name is Alberto Becerra, and I'm going to talk about simple diffusion, end-to-end diffusion for high-resolution images. In this presentation, we are going to cover the motivation of the work, the experiments performed in it, and the conclusions which can be extracted. Diffusion models have proven highly effective for generating images, audio, and video. This work seeks to enhance noise reduction in high-resolution images without overcomplicating the model. It revolves around a key question. Is it possible to train conventional diffusion models on high-resolution images and achieve results as effective as those from alternative methods? The drawback of existing techniques is that they add complexity and generally do not allow for a straightforward end-to-end training approach. The authors show that it is possible to train a single denoising diffusion model for resolutions up to 512 with only a small number of modifications with respect to the original formulation. Diffusion models are a type of deep generative model that have recently drawn considerable interest in computer vision due to their impressive ability to generate images with fine details and high diversity. The unique aspect of diffusion models is their probabilistic framework, which involves learning to reverse a process that adds increasing levels of noise to the training data. This approach has two main stages, forward diffusion and backward denoising. In forward diffusion, noise is gradually added to the original images over a series of steps, degrading them to the point where they look like pure Gaussian noise. If we consider this process as Markovian, then we can parameterize the transition probabilities as seen here. The subsequent backward denoising phase reverses this process, iteratively removing noise to reconstruct the original images. At inference, images are generated by gradually reconstructing them from random white noise, with the noise removal at each step estimated by a neural network, typically using a unit architecture to maintain dimensional coherence. Experiments are performed on ImageNet, a standard in vision models benchmarking. A widely used metric for image generation is Fréchet inception distance. It basically compares the distance of the 2048 size features obtained after applying Inception v3 backbone to a reference dataset, in our case ImageNet, and also to the generated images, then fitting Gaussians on them and computing the Fréchet distance between them. The alpha cosine noise schedule is commonly used in diffusion models for image generation as it maintains consistent variance through the diffusion process. It was initially designed for low-resolution datasets like CIFAR10 with 32 x 32 resolution and ImageNet with 64 x 64 resolution. However, for higher resolution images, this schedule may not add enough noise early in the process, leading to issues in denoising. For example, when applying this schedule to a 128 x 128 image, it was observed that the image structure becomes visible early on in the diffusion process, suggesting that the generative model has less time to make global decisions. This is because it undergoes downsampling to a 64 x 64 image via average pooling. The diffusion distribution of the downsampled pixels has half the noise variance, creating a higher signal-to-noise ratio. The signal-to-noise ratio for a downsampled image of size s times s is s squared, times greater than the full-sized image. Given this effect, we can adjust the noise schedule to compensate for higher resolution. As can be seen in Table 2 for ImageNet at resolution 128 and resolution 256, shifting the noise schedule considerably improves performance. The difference is especially noticeable at the higher resolution, where the difference is 7.65 for the original cosine schedule against 3.76 for the shifted schedule in FID on the trained data. Notice that the difference in performance between the shift towards either 64 and 32 is relatively small, being slightly better for the 32 shift. Dropout, where we randomly turn off certain neurons during training, is a popular method, but it's typically avoided in high-resolution models due to performance concerns. Instead of applying dropout throughout the whole network, it was used selectively. A starting resolution is set to define where dropout begins. For example, if the starting resolution is 32, we apply dropout only to layers at 32, 16, and 8 resolutions. This approach leaves the higher resolution layers intact, reducing the risk of overfitting without sacrificing model stability. Applying dropout, in every case, did it better than not applying it. When we applied dropout, starting at 64, 32, or 16 in experiments with 128 resolution images, the outcomes were similar. Two things that can be noticed are, first, that applying no dropout at all leads to overfitting, and second, that starting dropout at the same resolution as the data is too aggressive, leading to instability. In this part, let's explore what happens when we increase the number of 16 times 16 network modules in a unit architecture. In units, the number of blocks generally refers to the building blocks in the downward direction. When you see a notation like 2 plus 3 blocks, it means that there are 2 blocks going down and 3 blocks coming back up. Why do we focus on scaling at the 16 resolution? It's a practical choice for both space and time efficiency. Plus, it's a key resolution where self-attention is commonly used in diffusion models, as seen in many studies. Generally, increasing the number of modules tends to improve performance, as shown in Table 4. However, the FID slightly worsens when we go from 8 to 12 blocks. This drop in FID might mean that we need more regularization as the network grows, especially in larger UBIT architectures. Let's start with a typical unit designed for 512 resolution images. From there, downsample is done to either 256 or 128 using convolutional layers of the discrete wavelet transform. The main hypothesis is that downsampling should not only maintain sample quality, but also improve the model's efficiency. The results are surprising in this sense. Models with downsampling not only run faster, but they also produce better quality samples. It seems that by downsampling these high-resolution feature maps, we allow the network to focus on what matters most, leading to more efficient optimization and better output. This approach also helps avoid the performance issues that can arise when dealing with excessively large feature maps. Multiscale loss is a correction over the standard loss. This correction tries to reduce the effect of dominating high-frequency details in high-resolution images. To do so, it evaluates the standard training loss at downsampled resolution with a weighting factor that increases for the lower resolutions. As the picture in the table, at the 256 resolution, the multiscale loss didn't make much of a difference. In fact, it slightly underperformed compared to the conventional loss. But when we moved to the higher resolution of 512, the multiscale loss showed a significant impact. This suggests that the multiscale approach might be more effective at higher resolution, where focusing on broader frequency ranges can enhance the model's performance. Finally, a comparison against other models in the literature is performed. These models don't use any guidance or other sampling tricks like rejection sampling to get a clearer sense of how well the models are inherently performing. Using these modifications can sometimes lead to artificially high visual quality scores. Interestingly, the larger UVIT models performed very well in terms of training FID and inception score, surpassing all other methods reported in the literature. However, when evaluating on test data, the unit models had better FID score. This might reflect that increasing model size doesn't always improve eval FID. Overall, Simple Diffusion achieves state-of-the-art FID scores for class conditional ImageNet, and this is an exciting result because it suggests that with some adjustments to the diffusion schedule and loss function, Simple Diffusion can achieve high performance even at large resolutions like 512. And finally, to conclude, we have seen that the Simple Diffusion model outperforms many existing approaches in terms of FID and inception score on ImageNet without using guidance or other sampling modification. The multiscale loss, which emphasizes lower frequencies in the image, has a significant impact on the model performance at higher resolution. In addition to this, downsampling methods help to redistribute high-resolution blocks to lower-resolution ones, significantly improving model efficiency without compromising sample quality. It also reduces the need for larger feature maps. thus enhancing training efficiency and speed. The main drawback that we have found when studying this paper is that while the simple diffusion model demonstrates strong performance without using guidance or other sampling modification, it may not be as flexible in handling more complex image generation scenarios, where guidance or other specialized techniques can offer improved control or customization. Thank you for your attention.